To all of you joining me this morning, thank you for doing so. I'm Mr. Ish. As you can see, we're doing something different now. We're going to be posting some chemistry videos just for a variety, and because this right here is a big hang up for many students, we can always look at some problems here and there with regards to the topics that are related to high school chemistry. We have here ahead of us a reaction of combustion. We have butane, C4H10, being combusted in the presence of oxygen. And you know carbon dioxide and water are the end results. There's 25 grams of butane, 25 grams of oxygen, and we have an actual yield, everything here with regards to carbon dioxide, our main product that is being assessed, of 32 grams. How is it possible that we're dealing here with gases but we are looking here at grams? Well, it's possible. You could have a pre-measured or pre-weighted cylinder and you pump it in with gas and you can measure the weight of that cylinder afterwards and you can get the change in the mass of that cylinder, which would give you a good strong estimate of the amount of gas in terms of grams that has been pumped in terms of the reactant. So we're looking at all of that. Everything here with regards to STP, many of you will know that to be standard temperature and pressure, 273 kelvins, 1 atmosphere. Our goal here is to determine the theoretical yield, the limiting reagent, the percent yield, and the volume of CO2 generated after the reaction is complete. Consider the reaction to be going in only one direction because as the reaction is proceeding, the carbon dioxide is being funneled away, so there's no expectation that the reaction will go in the reverse direction because the product is being removed from the system. 25 grams, and actual yield 32 grams carbon dioxide. The first thing you want to do is balance the equation, and we have to do that because without that your reaction values, everything will be wrong. You're seeing 4 carbons and 1, or here you'll put a 4 here. You have 10 hydrogens, you have a coefficient here of 5 which will give you your 10 hydrogens, but your oxygens will be off. You'll have 5 plus 8, 13 oxygens. Here if you put 13 over 2, it will give you what you want, but you still have to balance it and get rid of this fraction. Cross multiply the fraction everywhere. You'll have 2C4H10 plus 13O2. You can have an 8 CO2 plus 10 H2O. Now verify everything. I have 8 carbons, we're good. I have 20 hydrogens. I have 8 times 2, 16 plus 10, 26 oxygens, and 13 times 2 is 26. So my equation is balanced and everything looks good. These are my coefficients. And I'm going to put them right over here in a different color. Why not? 13. Here I have an 8. And here I have a 10. And that represents a balanced equation and the procedure is good. Now let's get to our question. Now we have to determine the limiting reagent. We have 2 reactants, butane and oxygen. How can you do that? Well, let's talk about butane, and I'm going to symbolize that as a B. I have here 25 grams. 25 grams of butane. What's the molecular weight? Well, you'll have to bring out the periodic table and calculate it. You'll have 12 times 4 plus 10, or 58 grams per mole of butane. What about oxygen? You have 25 grams of oxygen, but this is O2, divided by 32 grams per mole of O2. You have to do this calculation. Whichever one is a smaller number, that right there is your limiting reagent. 25 divided by 58. I'm getting 0.431 over here. 0.431 mole butane. Let's do this. 25 divided by 32. I'm getting here 0.781 mole O2. Which one's my limiting reagent? Right here, butane. And that question has been answered. Butane is your limiting reagent because it's a smaller value. We're going to use the butane value now to determine everything else. And do we need this oxygen part here? No, we don't. We can erase that because we've determined our limiting reagent. Your limiting reagent is butane. 0.431 moles of butane reacts. And everything here we're doing is determination of carbon dioxide reacts with 8 moles of CO2. Where is this 8 coming from? It's this. For each 8 moles of CO2, you're utilizing 2 moles butane. I'm trying to determine here the grams of carbon dioxide generated because that'll give me my theoretical yield. If this reaction was carried out under perfect of conditions and efficiency would have a theoretical yield. We would compare that theoretical yield with this actual yield, 32 grams, to determine our percent yield. And each mole of carbon dioxide is 44 grams per 1 mole CO2. 44 grams per mole CO2. We could have written that a little better, but let's just keep it as this. Now look at these numbers and see and the units how things will cancel out. Mole butane, mole butane, mole CO2, mole CO2. You'll multiply these numbers on the top, divide them by 2, and that'll give you your grams carbon dioxide produced. 0.431 times 8 times 44 divided by 2, I'm getting 75.856 grams. 75.86 grams CO2. That is going to be my theoretical yield. Theoretical yield here being measured in grams. What was our actual yield? 32. Now how can we determine our percent yield? Percent yield is always equal to your actual yield divided by theoretical yield. Our actual yield is 32, but we could have really gotten 75.8, which means whoever carried out this reaction did it under poor conditions, and their reaction measurements were not perhaps good, and they lost a lot of materials along the way, and they had a wasteful process. So you do 32 divided by 75.86, multiply that by 100, we have a yield here of 42.18%, a very poor yield. 42.18%, but still that answers our question. We've determined our limiting reagent, which was this. We've determined our theoretical yield, which is this, and now percent yield is this. Now the last thing which remains is this volume CO2 generated, and we can do that. You have to think back right here, the standard temperature pressure, ideal gases, assuming we're generating ideal gases, a 1 mole of an ideal gas under standard temperature pressure of 273 Kelvin in 1 atmosphere will always have a volume of 22.4 liters. That's something you memorize. 1 mole of that gas will occupy 22.4 liters. Well, since we're talking about carbon dioxide, how can we determine its volume? You would have had to determine the moles of CO2 generated. That's exactly how you would do it. And you'd be looking here at your actual yield, because that's exactly what was generated, not your theoretical yield. You look right here, 32 grams of CO2 divided by 44 grams per mole, which is your molecular weight of CO2, multiply this by 22.4. That'll give you your moles of CO2. You multiply that with 22.4 liters, which will give you exactly how much volume this carbon dioxide is, assuming 32 divided by 44 times 22.4. 16.29 liters. That right here will be your answer. I'll put it right here, 16.29 liters. Under standard temperature and pressure conditions, the volume of CO2 generated based on this value over here will occupy 16.29 liters. Under standard temperature pressure conditions, 1 mole of that would have generated 22.4, but you don't have 1 mole of that, you have 32. If you had a mole of it, at least it had to meet a 44. But based on this theoretical yield, if you had the complete yield, 100% yield, then you would do 75.86 divided by 44. In that instance, you'd have 1.72 moles of carbon dioxide generated. You multiply that by 22.4, and in that instance, you'd have 38.6 liters of space being occupied. But here we have 16.29 because we again generated less than the desired amount. That less than desired amount translates to less than the final volume as well. And that right there answers everything for us in this particular compound question. You see, start with the balanced equation, find your limiting reagent, and use a limiting reagent to do all of your calculations. Thank you for joining me. Have a good day.